Math 1143, Section 3.6, Modeling with Exponential and Logarithmic Functions. First, in Objective 1, we solved some literal equations for specified variables. In this first one, solve the equation r equals 43 plus 216 times e raised to the exponent k times t. Solve for the variable k. Okay, so k is in an exponent. So first we want to isolate e to the kt. So first subtract 43 from both sides. So r minus 43 equals 216 times e to the kt. Then divide both sides by 216. So we get r minus 43 all divided by 216 equals e to the kt. And now we can take the natural log of both sides, or equivalently we can convert this exponential equation into its logarithmic equivalent. Either way, if we just take the natural log of both sides, we get the natural log of r minus 43 over 216 equals the natural log of e to the kt, but the natural log of e to the kt is just kt. And now we're just one step away. Divide both sides by t, so k is equal to the natural log of r minus 43 over 216, all divided by t. Okay, in the next equation, solve q equals 76 minus 15 times log base 7 of m plus v. Solve for the variable v. Okay, so this time we want to isolate log base 7 of m plus v. So we can subtract 76 from both sides, so we get q minus 76 equals negative 15 times the base 7 logarithm of m plus v. Then we can divide both sides by negative 15, and we get q minus 76 divided by negative 15 equals log base 7 of m plus v. And then we can use both sides as an exponent for a base 7 exponential, right? Remember, a logarithm is just an exponent. So in other words, 7 raised to the q minus 76 over negative 15 is equal to 7 raised to the base 7 logarithm of m plus v. But 7 raised to the base 7 logarithm of m plus v simplifies to m plus v, just using the definition of a logarithm. So we can write this as 7 raised to the exponent q minus 76 divided by negative 15 equals m plus v. And then finally, to solve for v, we just subtract m from both sides of that equation. So v is equal to 7 raised to the exponent q minus 76 over negative 15 minus m. Okay, it doesn't look very pretty, but it doesn't have to. Okay, in the next one, solve the equation the natural log of k divided by a equals negative e divided by rt. Solve this for k. Okay, so on this one, k is in the argument of the natural log, so we can use both sides of this equation as an exponent for the base number e, since it involves the natural log. So that is e to the natural log of k divided by a equals e raised to the exponent negative e over r times t. But e to the natural log of k divided by a simplifies to k divided by a. That's just based on the definition of the logarithm. So k divided by a equals e to the negative e divided by RT. And we want to solve for k, so now we just multiply both sides by a, and we get k equals a times e to the exponent negative e over RT. Okay, so that's our solution. Okay, now we'll move on to objective 2 in section 3.6. So we'll just read some information. So we're going to learn how to create models for exponential growth and decay. Recall from section 3.2 that if b is a constant real number such that b is greater than 0 and not equal to 1, then for any real number x, a function of the form y equals b raised to the exponent x is called the base b exponential function of x. And note that if b is greater than 0 and b is not equal to 1, then b is equal to e raised to the exponent, the natural log of b. That equation, b equals e to the natural log of b, is just an application of the definition of a logarithm. To wit, the base e logarithm of b, which is the natural log of b, according to the definition, that's the exponent that e must be raised to in order to produce b. Okay, so that's not a surprise. Note that if the base number b is between 0 and 1, the natural log of b is less than 0, which is to say that the natural log of b is negative when the value of b is between 0 and 1. Also note that if b is greater than 1, then the natural log of b is greater than 0. In other words, the natural log of b is positive when b is greater than 1. We already know that if b is between 0 and 1, then the exponential function y equals b to the x is decreasing. It's a decreasing exponential function. Therefore, if the natural log of b is negative, then y equals the natural log of b times x is a decreasing exponential function. So y equals e to the natural log of b times x is equivalent to y equals b to the x because e to the natural log of b is the same number as b. Okay, we also know that if b is greater than 1, then the exponential function y equals b to the x is increasing. Therefore, if the natural log of b is positive, then y equals the natural log of b times x is an increasing exponential function. Okay, so none of this should be a surprise. It might take a few minutes to process it. On the next page, we define the continuous exponential growth and decay models. But first, observe that an exponential growth model will involve an increasing exponential function, and an exponential decay model will involve a decreasing exponential function. That is just a statement of the obvious. Okay, we'll continue then. The continuous exponential growth and exponential decay models. Since many exponential growth and decay models are functions of time, the domain variable t is used instead of x. Any variables may be used, but some variables are more suggestive than others. For both exponential growth and exponential decay, we may use this equation for the model, y equals y sub 0 times e raised to the exponent k times t. In both cases, y sub 0 is the initial value of y when t equals 0. So first we'll discuss continuous exponential growth. Okay, so if y equals y sub 0 times e to the kt is exponential growth, then it must be the case that k is positive, k is greater than 0. When k is greater than 0, k is called the continuous exponential growth constant, or just the growth constant, or sometimes it's referred to as the growth parameter. If in this setting of continuous exponential growth, a growth rate parameter is given as a percentage, then the number k is the decimal form of that percentage. Okay, so just be on the lookout for the different terms used to describe k. And then analogously, we'll discuss continuous exponential decay. If y equals y sub 0 times e to the kt, k must be negative or less than 0 if it's exponential decay. Okay, so when k is less than 0, k is called the continuous exponential decay constant, or just the decay constant, or decay parameter. And if in this setting of continuous exponential decay, a decay rate parameter is given as a percentage, then k is the negative of the decimal form of that percentage. Other variables may be used, as was mentioned previously, and if you prefer to use other variables, that is fine. Just be consistent and don't break any rules. We already know one continuous exponential growth model. So, for example, suppose a principal of $P is invested into an account with the annual interest rate R in decimal form. If interest is compounded continuously, then the amount of dollars A in the investment account after T years is A equals P times E to the R times T. And in this growth model, R is used instead of K. But if R is positive, which it should be if your investment is growing, then R is the continuous exponential growth constant. But in this setting, it's referred to as the interest rate in decimal form. Okay, in the next page, we will do some examples. The process in this one is sort of a run-of-the-mill type of situation. So suppose the initial quantity of a substance is 158 grams. After exactly 6 years, the quantity of the substance grew to 214 grams. So if we assume continuous exponential growth, we can find an appropriate model. So first, let's just write y equals y sub 0 times e to the kt. And we're told that the initial quantity is 158 grams. So y sub 0 equals 158. And then we're told that after 6 years, the quantity of the substance grew to 214 grams. So in other words, we can say when t is equal to 6, y is equal to 214. Okay, so what we do is, what we're trying to do is determine what k is. We already know what the initial quantity is. So we replace y with 214, set that equal to 158 raised to the exponent e to the 6k. And then we just solve this for k. So first divide both sides by 158. 214 divided by 158 equals e to the 6k. Then take the natural log of both sides, the natural log of 214 over 158 equals the natural log of e to the 6k, which is just 6k, and then divide both sides by 6. We'll continue this in